So in the previous video we were trying to see what is the sampling distribution of B1, and we had got to the point where we had found the value of SB1 as S over sigma xi minus x bar. So we got until here, and then we needed to do a hypothesis test in order to see if beta 1 and beta naught are equal to 0 or not. But before doing that, we have to talk about a few things like why. So we're going to use a t-distribution to do the hypothesis test, not a standard normal distribution. So we're going to see why that is and things that we'll need to do the hypothesis test. So first thing, there are two cases when we do like the interval estimates and hypothesis test. Those are if sigma, that is the standard deviation, is known or it is unknown. So whenever it is known, we do we use Z statistic, we do Z test, but since in our case the standard deviation is unknown, since we're using samples and not the actual population, our sigma is unknown, and that is why we were using the estimator for this distribution here. This one it's usually supposed to be sigma here, but since we are not working with the population, we're working with the sample. That's why we have S, and we're dealing with this case. And whenever sigma is unknown, we use the t statistic instead of the regular z statistic. In many cases where the distribution is not normal, or we don't know what the distribution is for the sample, we use t distribution. Or in other words, we can say whenever sigma is unknown, we use basically the estimator, and then whenever that happens, the margin of error and the interval estimates for the population mean, they are all based on t distribution, and t distribution is applied wherever the population variables, like population parameters, deviate from the normal distribution. And then t distribution is based on degrees of freedom, and as degrees of freedom increase, t distribution starts to resemble a z distribution, which is a standard normal distribution. So that is why we use degrees of freedom. So for every degree of freedom, let's say 1 or 2 and 3, and they keep increasing, there are different t distributions. So one would be that, one would be that, maybe one would be that. So this is degree of freedom 1, and this is the outer one is the degree of freedom 3. So as you keep increasing them, like there would be a point where enough degrees of freedom, the t distribution would look exactly like z distribution. So that is why we use t distribution whenever we don't know what the standard deviation is of the normal. Also, another thing to see here, the statistic that we call t alpha by 2, oopsie. So if we have that, oh, that's a pointy graph, that let's say this is our 0, this is t, let's say somewhere here we have t alpha by 2, and this is t minus alpha by 2. This area here under the curve is alpha by 2. So whenever we are going to use like t alpha by 2 anywhere, what that's going to mean is that so it's a t value. T alpha by 2 is the t value with area alpha by 2 in the upper tail, which is here, right? So that is a statistic we'll be using, like graphically this is what it represents. Now usually the interval estimate or the confidence interval, if sigma is known, it is something else, but when sigma is unknown, which is going to be our case, in the hypothesis test or interval estimation of beta naught and beta 1. It is going to be, the usual form of it is that whatever the estimator is, you get the the expected value of the estimator. So the expected value of the estimator plus minus the t statistic, t alpha by 2. There's going to be a nu here for degrees of freedom, but we can also take it off, doesn't really matter. And then it's multiplied by the standard error of the estimator. That's the general form for the confidence interval. So in our case, what that's going to look like is the expected value of b1 plus minus t alpha by 2. Then this is going to be the standard error of b1, or we can also write it as beta 1 hat plus minus t alpha by 2, and then standard multiplied by standard error of beta 1 hat. That's going to be the confidence interval. And the good thing is going to be that we'll not have to calculate this value here. It will be given, so when we do the analysis in R, the summary that it gives us, it's going to have these values, but some will calculate, some it'll have. So we'll take a look at that later though. And this here is nothing, it's just SB1 that we had calculated. So if we look up there, this is the value that we're going to use. And if you don't know what S here is, you're going to have to watch a previous video. And this T alpha by 2, what we're going to do about that is, so the T stat, that's the original formula from hypothesis tests, S over root n. So basically this is supposed to be here the estimator, the expected value of the estimator. This is got to be the population parameter, which is mu naught. In our case, it'll be the actual value of beta 1 when we're doing the hypothesis test. And down here is the error, which is going to be SB1 again. So if we find the value of t here for our case, it is going to be b1 minus beta 1 over SB1. That's going to be the value. And the hypothesis test is going to be dependent on this statistic. And we're going to see two approaches, p-value approach and the critical value approach, that is the t-value approach. But the hypothesis test that we are going to do is going to be checking the equality that our beta 1 is equals to 0 or not. The thing is, when we're checking that it's equal or not equal to something, then it becomes a two-tailed test. If we check if it's like less than equal to 0, less than equal to 0, or when we are checking then this is a one-tailed test. But since we're just going to be using a two-tailed test, we're just going to focus on that.